SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering, Module 2, Vapor Power System Part 3. So, in this lecture, our main focus would be to deal with contents of fuels and combustion. So, the word fuels in a steam power systems is derived from the word that is coal or any kind of fuel oil. Either it can be liquid fuel or it can be also to some extent gaseous fuels, but main constituents is for coal. But to deal with this coal, we need to review some of the thermodynamic aspects, and that is derived with certain concept in defining the certain parameters. These parameters are heat of combustion, then heating value of the fuel, combustion temperatures. Then we having defining all these parameters, we will be able to find how this combustion reactions happens for the coal, and to some extent we will deal with some of the liquid fuels and biomasses, how they are characterized. But our main focus would be for coal combustion. Before you go to that coal part, let us try to understand or review some of the basic concepts of thermodynamic systems, that is closed and open systems. As you see here, the closed systems does not allow the mass and energy interactions to be possible. So, it only allows that a system is having its own boundary, and whatever energy which is in the systems, that is mainly with internal energy. Whereas in a open systems, it allows both mass and energy interactions, and for which the system is defined in terms of control volume. Now, in same philosophy, if you try to look at a reactor in which this combustion is going to happen, for example, you can view a reactor as a container in which there is a entry for carbon and oxygen at certain reference pressure and temperatures, but out of this reactor, that means once the carbon and oxygen they react each other, the reactor gives out the product which is carbon dioxide, but at same reference pressure and temperatures. What I am trying to say here, such a systems can be either viewed as a closed systems. So, when you deal with the reactions that is happening within the reactor, then we can take it as a closed systems. But if you deal with complete systems involving entry of carbon and oxygen and exit of carbon dioxide, then you can view it as a open systems. With this philosophy, heat of combustions, which is normally represented as a energy interaction as heat for a thermodynamic systems, is interpreted as heat of combustions. So, here heat release interpreted as a heat of combustion. Now, with this basic philosophy, let us try to define the what do you mean by heat of combustions for open systems. So, if you refer this figure, so basically this carbon and oxygens are treated as reactants, and the products, that is CO2, they are treated as the output from this reactor is CO2, which is treated as a products. And through this process, if you hypothetically say there is some heat is coming in and there is a work transfer, then complete equations can be represented, that is first law for an open systems. We can write is enthalpy of reactants, total enthalpy of reactants plus total energy which is entering and enthalpy of products, then the work transfer for this reacting systems. Now, if you split these reactants, that can be reactants can come up with many number of constituents. So, it is a summation of all the reactants with its corresponding mass and enthalpy, and rest of the parameter remain same. Now, this mass can be represented in terms of number of moles and the molecular weight of those components. And here the enthalpy is represented as HF, and we call this HF as enthalpy of formation. So, this is how we view this enthalpy of formations, and later point of time we will see this and how this enthalpy of formation is related to heat of combustion. Now, let us see same concepts like for example, if you say the combustion of ethane, and ethane takes 3.5 times O2 to form CO2 and H2O. It is a complete combustion for which CO2 and H2O are the final products. Now, if you want to define the concept of formation of enthalpy of heat released during this formation, then let us try to understand how ethane is formed. So, if you take a reference condition of 1 atmosphere at 20 and 25 degree centigrades, then the chemical formula for ethane is C2H6, and where 2 carbon atoms reacts with 3 molecules of hydrogen to form ethane, and during this formation of ethane there is a heat release, that is 2817.3 kilojoule per kg. Similarly, enthalpy of formation of CO2 can be interpreted as 8946.8 kilojoule per kg. This is the experimental evidence, and when there is a plus sign here, and we call this as its exothermic reactions. So, we can say that heat released during this formation is negative quantity, which is minus of this, and this is how the enthalpy of formation is related to an exothermic reactions. Now, same thing for a closed system if you want to interpret. For instance, if you arrest that already reactants are, there is no entry for reactants and no entry for products, and we say that this both reactants and products are within this reactor. So, you will replace this reacting system as a simple closed system reactor, and this, so that this delta W and delta Q will be 0. Then entire heat release, that means both reactor which contains already the, that is which already contains this fuel plus air. So, when they react each other, it produces energy, but that energy is arrested within this reactor itself, and that is interpreted in terms of rising its internal energy. And such a thing, since there will be, since in this case there is no work output, so it is a non-flow work, and such an example can be interpreted as a like a bomb. So, bomb means already fuel and air is, fuel is there, and when you just ignite this fuel, it releases the energy. So, it is a explosion of bomb can be treated as a fuel burning in a closed system. So, same philosophy we can also analyze how much internal energy changes during this process. So, for this closed system energy, we can write closed system reactor, we can write the first law of thermodynamic equations in terms of internal energy, which is for reactants, and that is for products, and in this process there is delta Q and there is non-flow work, and since both the terms will not be there by neglecting this there is no flow work and no this may be heat release. So, this heat release is interpreted as change in increase in the internal energy. So, Basically this UR can be replaced as H minus PV, and PV means it is flow, PV means you can interpret as an ideal gas, we can write N R0 times T, and for reactants, and the from the right hand side we can write this as a products. N stands for number of moles, total number of moles remains same, and same analysis of open systems can be extended for closed systems by writing this enthalpy as H is equal to U plus PV. So, that U can be represented in terms of H and PV. So, this is how the closed system analysis is done to interpret heat of combustion. Now, talking to having said all these things, we are now in a position to define the heating value. Normally, the standard practice is not to define the fuel potential in terms of heat of combustions, rather fuel potential is defined by the unanimous parameter, we call this as a heating value. So, normally there are two types of heating value that is interpreted, one is higher heating value, other is the lower heating value. Now, why there is a difference? Because the difference lies that the heat release of water vapor in the products. So, if you see our earlier reactions, in a complete combustion reactions, always there is a formation of water. Now, if this water vapor enthalpies of this water vapors are taken into account, then we call this as a higher heating value. If it is not taken into account, it is called as lower heating value of the fuel. So, heating value is defined at the heat released for a complete combustions that begins at standard temperatures, that is 25 degree, and the products of the combustion are cooled to same temperature in a steady adiabatic systems without involving work. So, basically we can recall the equations for an open systems and arrest the term like delta W as 0, that means no PDV work, and delta Q is, we call this as a heating value, that means heat released during these combustions, and that is nothing but the difference between the reactants, total enthalpy for reactants and products. So, HB, heating value of the fuel, is negative signs of delta Q, which is delta Q is nothing but the negative of heat of combustions. So, that is the reason heating value is the just a negative of heat of combustions. So, just to make ensure that heating value is always treated as a positive quantity. So, heat of combustion is mostly negative for an exothermic reactions, but always when you define this heating value, it is just negative of that heat of combustion. So, that it always remains, that means heating value is always interpreted as a positive quantity. Now, this is also I have explained that heating value for an open system is nothing but the enthalpy of combustions, and we have higher heating value, we have lower heating value. Further point I need to mention that the heating value depends on whether the reactant fuels are in the liquid or vapor state, and it because it takes certain quantity of energy to vaporize the liquid fuel. So, as long as complete combustion occurs, the heating value of the fuel does not change. When you say heating value of open system, it is nothing but heat of combustion. When you say heating value for a closed systems, it is known as internal energy of combustion. That means it increases the only internal energy. So, with this philosophy, now we are going to, with this thermodynamic background, now let us see that how we were going to deal with the, or how you are going to calculate this heating value for coal, and this coal is the main source of energy for the steam power systems. Normally for the coal, we say heating value as calorific value of the coal, either you call this entering value or calorific value of the coal, and it is the property of fundamental importance which is defined as the heat transferred when the products of complete combustions of a sample of coal are cooled to initial temperature of air and fuel. And to do this, we need to have a standard test which is done with a bomb calorimeter, which is a device that measures the heating value of the coal. Now, here also for the coal, two heating values are also cited, higher heating value and lower heating value. So, higher heating value assumes that water vapors in the products condenses, and thus it includes the heat of vaporization of water vapors formed by the combustion. Whereas, lower heating value assumes that water vapors formed by the combustions leaves as vapor itself. So, its value is further reduced by a quantity which is enthalpy of vaporization. So, there are a lot of researches and lot of analysis was done. People have tried to find out some experimental evidence using this bomb calorimeter, and side by side there are analytical analysis for the coal, for variety types of coals which was done earlier. And one most important formula which is defined, which is called at Dulong-Petit formula, means previous lectures I have also explained similar formula for Dulong's formula, where the heating value was expressed in terms of BTU per LBM. But here in SI units, this Dulong's formula was modified with Dulong and Petit formula, and this formula is used to estimate higher heating value of anthracite and bituminous coal. So, this formula is mainly used for anthracite and bituminous coal, and but this formula is not generally used for low grade fuels, it is for high grade fuels, because its value underestimates. So, for that things the Dulong-Petit formula says that in an ultimate analysis, when we say that the coal contains carbon, hydrogen, oxygen and sulfur. So, for these 4 items, because they only take part as a combustion reactions. This formula states that once you know their mass fractions, then heating value of the fuel can be expressed by these expressions, and this expressions was routinely used and tested using bomb calorimeter for various coal samples, and finally this formula was unanimously accepted. So, for a given coal and ultimate analysis, if you know their constituents, then we can find out higher heating value. Once you know this higher heating value, we should be able to calculate lower heating value of fuel by subtracting from mass of water vapor multiplied with enthalpy of vaporizations. Now, enthalpy of vaporization for water, if you take into account, so that this becomes HSV minus 2.395 mass into MW. So, basically speaking, if you know the mass of water, then we can we can calculate the heating value, lower heating value of the fuel. Then let us move on to next parameter, which is called as combustion temperatures. So, always we say that when a reaction happens, there is a heat release. Of course, when a heat release is taking place and we are trying to see during a combustion process what is the upper limit of temperature that can happen during a heat release, during this kind of heat release processes, and mainly for kind of fossil fuel situations. So, to define that, we call this as a combustion. We just need to define some parameter which is called as combustion temperatures. One frequently used parameters is nothing but the adiabatic combustion or adiabatic flame temperatures. So, what it means that the normally heat of combustion for gases has effects in increasing the enthalpy for an open systems and internal energy for the closed systems. Through this increase in enthalpy of increase or internal energy increase, the temperature also increases. Now, if you look at the temperatures that released for a flue gases, they are interacted with various heat transfer surfaces of the components like water tubes, superheaters, reheaters of the steam generator unit. So, one way to design such kind of components, we just have to have an estimate that what is the upper limit of temperatures that this component has to face and during phase from the flue gases. For this reason, it is very essential that you define this upper limit of temperature, and we call this as a adiabatic combustion or adiabatic flame temperature. So, what does this adiabatic flame temperature mean? So, it is defined for a combustion medium as the maximum temperature that we can obtain either for an open system or closed systems. So, in a sense that adiabatic flame temperature is defined for an open systems and for an closed, can be defined for an open system as can be closed systems as well. So, in one way we need to define the adiabatic flame temperatures typically on a for a constant volume process and for a constant enthalpy process. So, for an open systems, if you say maximum temperature we can arrest, that means if you recall this, the combustion equations for reactants products involving heat transfer and work transfer, this is the general equations: total enthalpy delta Q, total enthalpy of reactants delta Q, total enthalpy of products delta W, work transfer. By arresting these two values as 0, we write this equation as this, and when this enthalpy of reactants and products they are equal, under those circumstances whatever temperature rise can happen within the reactor, we call this as a adiabatic flame temperature or adiabatic combustion temperature at constant pressure. Now, when you interpret same concept for an constant volume systems, we replace these equations in terms of internal energy. So, basically this internal energy is represented as H minus PV. So, for that we write same equations by involving considering PV is equal to RT nRT. So, we rewrite this equation in this form. So, in this form of equation also there is a non-flow of work which is 0 and this is also 0. So, based on this we arrive at this particular expressions which is for which enthalpy of reactants and enthalpy of products match. So, under that situations the maximum temperature that you can achieve is known as adiabatic combustion temperatures. So, if you recall or refer this particular figure which is talks about enthalpy and temperatures, and for one for reactants, other for products. So, basically there is a heat release. So, we have a negative sign here. So, we are looking at the enthalpy value in the negative directions. Now, if you keep on increasing the temperatures, the reactants vanishes and products are formed, and one particular point of time the enthalpy of reactants and product matches, and that coordinates of that point we call this as adiabatic flame temperatures. So, with this viewpoint, now let us see that how we can go for the combustion analysis for the coal. So, our main target for the combustion of coal, which means it is a high temperature oxidation with fuel elements. Now, if you take coal or any fuel oil which are nothing but the constituents of fossil fuel, they mainly contain on mass basis with components as carbon, hydrogen, oxygen, nitrogen, sulfur, moisture and ash. So, this was explained in our earlier lectures, the constituents of coal. Now, if you take their total mass, we can say C plus H plus O plus N plus S plus M plus A is equal to 100% by mass. But main issue is that out of these elements, the combustible elements are only carbon, hydrogen, sulfur. So, they can take part this oxidation process. And why we say nitrogen? Because nitrogen is already there in the air itself. So, if you see these combustible reactions with carbon and oxygen, so carbon plus oxygen gives CO2, hydrogen plus oxygen it gives H2O, sulfur plus oxygen gives SO2. And this is the situation for complete combustions. Now, when there is incomplete combustions, we may not get CO2, rather we can arrive at CO. That means, carbon does not get excess oxygen or it could not be oxidized to form CO2, rather it forms CO. So, under such situations it is an incomplete combustion, but our main philosophy is that we must supply sufficient oxygen for complete combustions. To supply now to get oxygen, we have to rely on air, because the reaction process normally we do not supply oxygen, rather we supply air. So, air requirement is very vital for a steam power systems. So, to burn the fuel completely, there are 4 conditions that should be satisfied. First, we should supply enough air for complete combustions, and when you say enough air, we should make a proper mixing of fuel and air. So, we require enough turbulence and thorough mixings. Then for this air and fuel mixing, your furnace temperature should be very high, or which can ignite the fuel and mixture. So, that means we should maintain very high furnace temperatures. Third thing is that we have to provide a large furnace volume to allow sufficient time for complete combustions. That means we have to allow large area or large volume, so that all the fuel components are burnt completely. But virtually although these are hypothetical statements, complete mixing of fuel and air is virtually impossible. For that reason, normally we have to bear with supplying excess air, so that necessity of oxygen can be realized during this combustion process. Now, let us try to analyze the oxidation processes of the combustible elements, that is carbon, hydrogen and sulfur. So, if you take a complete analysis with all the components by mass, so if you add them, C plus H plus O plus N plus S plus M plus A is equal to 1. Now, we say that out of these constituents, only carbon, hydrogen and sulfur take part in the oxidation process. Already oxygen is there, and to make their oxidation process, we have to supply oxygen. So, if you for a complete combustion of carbon with oxygen, we require that 12 kg of carbon. For 12 kg of carbon, the oxygen requirement will be 32 kg, because its molecular weight is 32, so that it forms 44 kg of CO2. Similarly, for hydrogen and oxygen combustion, we require 4 kg of hydrogen with 32 kg of oxygen to give 36 kg of H2O. So, likewise for sulfur, we require equal amount of sulfur, and that is 32 kg of sulfur and 32 kg of oxygen, it gives SO2, that is sulfur dioxide, that is 64 kg. Now, but our main role in this analysis is to find out what is our oxygen requirement. So, for example, if you say C kg of carbon, the oxygen requirement will be proportionately, that is 32 by 12, which is 2.67, and for H kg of hydrogen, oxygen requirement will be 8 H. For S kg of sulfur, oxygen requirement will be S kg. So, the total oxygen requirement for this combustible element would be 2.76 C plus 8 H plus S is this, but already coal contains 1 unit of oxygen, it is minus O. So, our requirement is this minus O already, because already some oxygen is present in the coal. So, this is the oxygen requirement, but then we cannot get oxygen directly for such a large amount. So, we have to rely on the oxygen supply from air, but again air contains 23% of oxygen by mass. So, correspondingly, for to burn 1 kg of fuel up for complete combustions, the total theoretical air requirement would be WO2 divided by 0.232. Then this is the final expressions, that is theoretical air requirement for coal. So, if you know carbon, hydrogen, oxygen, sulfur constituents by mass, total theoretical quantity of air can be calculated. Then, but actual quantity is something represented by excess air, because it is not always possible for a complete mixing. So, we always have to rely on excess air. So, when the excess air is supplied, we need to define another parameter which is called as a dilution coefficient, which is defined as ratio of WA by WT. Now, from this also one can calculate what is the excess air, percentage of excess air, that is WA minus WT by WT. So, this is this analysis will tell us that for a 1 kg of fuel, what is the requirement of air. So, this is all about the coal analysis. Now, let us talk something on liquid fuel, and this is a very conceptual, and we are not going deep into this because liquid fuels utilization is very rare for steam power applications, because we require very large quantity of fuels, that is which you can get from the coal. But however, liquid fuels are very much essential for combustion in IC engine, internal combustion engines, because technically these liquid fuels are excellent source of energy with nearly constant heating values, because whereas if you say coal, there are variety of heating values depending on the different grades of the coal. But when you say liquid fuels, they have a very nearly constant range of heating values. They are easy to handle, store and burn. Many a times the crude oils is refined, fractionally distilled, cracked into products with various formation like formation of gasoline, aviation fuel, diesel fuels, fuel oil, lubricating oils. All these things are obtained through various chemical processes. The other category of the fuels are also known as synthetic or syn fuels. They are the gaseous and liquid fuels that are produced largely from the coal and various waste or biomasses. Now, the conversion of coal to these fuels is obtained through gasifications or liquefacions. So, gasifications or liquefations are some of the techniques in which we can convert the coal into liquid fuels. Now, for such fuels, we define a parameter which is normally called as flash point, which is the lowest temperature that allows inflammable vapors to be formed, and it is found by heating the fuel slowly, sweeping a flame across the liquid surface and noting the temperature at which distinct flash occurs. So, there are flash point apparatus which can measure the flash point for any given fuel. The crude oils have low flash points and they require special handling procedures, but the most suitable crudes for direct burning of the sulfur contents. So, now coming back to more details on the liquid fuels, if you see the crude oil, they contains 83 to 87% carbon, 11 to 14% of hydrogens with varying amount of sulfur, oxygen, nitrogens and other particulate matters. And normally these liquid fuels are represented in terms of hydrocarbons with a molecular formula of CmHn. So, here M stands for number of carbon and N stands for number of hydrogens. But their linking or interlinking is done in variety of ways, like paraffins, or they can be olefins, they can be dilophenes, they can be cycloparaffins, they can also be aromatics, which is benzenes or naphthalene, and of course, this value of N depends on the M also. So, these are the chemical formulas for various hydrocarbon fuels, and when you deal with IC engine combustions, normally this type of liquid fuels are come into existence. And the last component is that deriving the fuel from the biomass. So, biomass we can call it as a renewable source of energy or is a alternative energy resources which we can obtain from plants. So, they are organic matters which is derived from the plants or which are grown in the land, or there can be we can get it through aquatics, they can be forest corpse residues, and they are specially and they can be animal manure. So, they are treated in a specific way so that the fuel can be used for variety of applications. Hence, they are treated as a renewable source of energy at par with solar energy, and it can because the solar energy is also utilized to grow the plants for these high energy contents through photosynthesis. Now, this biomass can be converted to liquid or gaseous fuels and thereby increasing its energy density and making it possible for transportation of long distances. There are possible ways of biomass conversions. One is biogas conversion route, other is thermochemical conversions, and third is biochemical conversions. So, in a bioconversions, it is a direct combustions or thermochemical combustion or biogas conversion as two routes. One is thermochemical conversions, which we call as a gasification or liquefations. Other route is anaerobic digestions and fermentations. So, for which we can create biogas plants and to produce methane and carbon dioxides with minimal impurities. So, this is grossly I have discussed about the liquid fuels, their utilities, their applications. So, this is all about the combustion fuels and combustions, and where our main focus would be solid fuels, which is coal. Now, with this we are now in a position to solve some numerical problems based on the coal combustion. So, the first problem is based on a coal analysis, and in our previous lectures we defined one of the auxiliary components of steam power systems, that is fans. So, there are two types of fan, one is forced draft fan, other is induced draft fans. So, the main distinction of these two fans is that forced draft fans normally handles only air because it supplies air requirement for the combustions, and induced draft fans is used to take the combustion products out of the plant. So, they mainly deal with the air requirement or air which is already present in the systems or various components. At the same time, it has to also take out the products of combustions. So, our main focus in the first problem is that we need to find out for a steam power systems, we need to find out what is the motor capacity for a forced draft fan which operates at 30 degree centigrade with following data. So, basically coal is coming from one end, which is a fuel, and for the coal the mass percentage are carbon 78%, hydrogen 3%, sulfur 1%, oxygen 3%, nitrogen 1.1%, water 3.3%, and coal feed rate is 10 tons per hour, and we require air from the atmosphere which needs to be sucked into the systems with excess air requirement of 30%, and this should be used to burn the coal. We also to calculate the fan power, we also require the plenum chamber pressure, which is already mentioned at 1.8 kilonewton per meter square, and mechanical efficiency at 65%. So, please recall our earlier lectures on fans, where we have written the expressions for power requirement of a forced draft fan, that is W dot F for forced draft fan is equal to m dot into V air, because it handles air, into delta P divided by efficiency of the fan. Now, out of this the expressions, we have data like delta P is already 1.8 kilonewton per meter square, eta F is equal to 0.65. Now, we need to calculate what is specific volume of air. So, specific volume of air, we can write it, get it from ideal gas equations, that is R T by P. So, you know R is equal to 287 and T is 30 degree centigrades, that is 303 Kelvin. So, we can write 303 divided by P is atmospheric, because 101,325 Newton per meter square, because we are taking atmospheric air into account, 101,325. So, this will give you specific volume for air is equal to 0.858 meter cube per kg. So, this is all the parameters are known, but we do not know what is m dot. So, m dot is mass of air requirement. So, mass of the air requirement we need to find stepwise. First thing we need to find out what is the theoretical air requirement for a coal combustions. So, you recall our expression, that is W dot T is equal to 11.5 C plus 34.5 into H minus O by 8 plus 4.3 S. Now, out of this we have already known this data that is given, C as 0.78, H as 0.03, S as O as 0.03 also, then S as sulfur as 0.01. So, putting this number, we can write W dot T is equal to 9.907 kg air per kg fuel. So, this is the stoichiometric requirement, but we are supplying excess air. So, total requirement of excess air will be 30% higher than this. So, we can say with excess air, 30% excess air. So, this W dot T would be 9.907 into 1.3. So, W dot T would be 12.9 kg air per kg fuel. Now, what is the fuel? Fuel flow rate, fuel supply is fuel supply or coal feed rate. Coal feed rate is 10 tons or 10,000 kg per hour. So, by putting this will imply what is mass of air requirement would be W dot T into 10,000 divided by 3600. So, this would be m dot air becomes 35 point, because you know this W dot T. So, this will be 35.83 kg per second. So, we have this m dot air requirement, then we can calculate W dot F, that is power requirement for forced draft fan would be 35.83 into 0.858 into delta P, that is 1800 Newton per meter square divided by 0.65. So, the power requirement for the forced draft fan would be 85132 watt, or approximately 85.132 kilowatt. Okay. So, this is how we calculate the power requirement for forced draft fan. Now, in the same problems we have just twisted that if for the same unit or same coal feed rate, if we need to use a induced draft fan that operates with a pressure differential of 2.5 kilonewton per meter square, and but gas temperature is 180 degree centigrade, fan efficiency is 55%. Then what could be the motor capacity? So, in our previous analysis we get m dot air requirement as 35.83 kg per second, and we also see that m dot gas is because the induced draft fan uses the combustion products. These combustion products are obtained from the rate at which the coal is fed. Coal is fed at the rate 10,000 kg per hour. So, from this we can calculate 10,000 divided by 3600. At this rate the combustion product or gaseous product or flue gas are generated. So, this gas means here it is flue gas. So, it is 2.78 kg per seconds. So, the total mass is we can calculate the sum of so m dot is m dot air plus m dot gas. Okay. Now, we also need to calculate the specific volume. So, specific volume of air we already know as 0.858 meter cube per kg, and so we can write V air is equal to R T air by P. Also for flue gases we say VFG is equal to R T flue gas by P. So, pressure, because flue gas, assuming that flue gas is released to atmosphere, so this pressure can be taken as equal. So, TFG is given as TFG is already given as 180 degree centigrade. So, we can find a relations like VFG is equal to 180 plus 273 plus 273 divided by 30 plus 273 into VAR, that is 0.858. So, flue gas specific volume will be 1.28 meter cube per kg. So, we are now in a position to obtain what is the power requirement for induced draft fan. So, W dot F for induced draft fan would be m dot air plus m dot gas into specific volume of the flue gas into delta P divided by efficiency of induced draft fan. So, here data is given, efficiency of is 55% and delta P is 2500 Newton per meter squares. So, by inserting the value we can obtain W dot F D, W dot, that is power requirement for induced draft fan, is equal to 22460 watt, or sorry, this number would be 224640 watt, or approximately 224.64 kilowatt. So, this is the first part. Second part is just to extend that how you can use Dulong-Pettit formula to calculate the heating value of the fuel. So, we recall Dulong and Pettit formula. So, already we have percentage of by mass for carbon, hydrogen and oxygen is given. So, you can recall this HHB as 33.83 C plus 144.45 H minus O by 8 plus 9.32 S. So, from question 1 we get the data as C is equal to 0.78, H is equal to 0.03, O is equal to 0.03, S is equal to 0.01. So, inserting this number we can find HHV as 30.27, because this unit is in megajoule per kg. This value would be 30.27 megajoule per kg. So, this is about linking this fan problem as well as the coal analysis. So, this is a good problem where it links where the different components of a steam power systems. Now, we will revisit another problem which was discussed in our previous lectures, which is called as fluidized bed combustion. So, fluidized bed combustion means in a combustion unit which is a fluidized bed. So, your initial state is that the coal particles create a initial state, the coal particles form a bed which is in the collapse state. Now, when the fluid is or air is inserted into the bed, it tries to spread. So, it becomes fluidized. So, now it becomes fluidized inside this chamber. So, for this fluidized conditions, our main requirement is that what is the minimum fluidization velocity, when it means to make this condensed state or collapsed state fluidized particle, collapsed state coal particles to become fluidized particles, fluidized state, what is the minimum velocity requirement. So, here basically there are three densities. One is density of bed, that is rho B, which is 1620 kg per meter cube. Other is density of solid, that is coal, that is 2780 kg per meter cube, and third is air, density of air, that which is we all know 1.2 kg per meter cube. In addition to that, we have viscosity of air, which is 1.8 into 10 to the power minus 5 kg by meter into second. And also the diameter of this fluid particles dp is 420 micron. So, with this data we are going to calculate what is the voidage and minimum fluidization velocity. So, first expression we recall as voidage, which is alpha is 1 minus rho b by rho s. So, it is 1 minus 1620 divided by 2780. So, voidage is a straightforward answer. We get the voidage at 0.417. Now, to go for the next study, that is fluidization velocity, we have to recall Reynolds number, and this Reynolds number has a empirical relations with a number which is called as Archimedes number. If you recall our previous lectures, the expression was written as for Reynolds number as C1 square plus C2 into AR stands for Archimedes number to the power combined to the power 0.5 minus C1. So, data for C1 is taken as 27.2 and C2 is equal to 0.048. Now, this Archimedes number AR is defined as rho A into rho S minus rho A G dp q divided by mu g square. So, all the data are given here, and when we insert these numbers we arrive at AR is equal to 7480. So, all this data is given rho b, rho s, g is 9.81 meters per second square, dp is 420 micron. So, putting this mu air, that is gas, that is given as 1.8 into 10 to the power minus 5. So, putting this number we get Archimedes number as this. Then we can rewrite this Reynolds number as rho Vd, that is minimum fluidization velocity, rho air because fluidization happens for air, that is dp divided by mu a, that is equal to C1 square 27.2 plus C2 0.048 into 7480 all to the power 0.5 minus 27.2. So, from this we can take um as so this value becomes 5.95. So, we say 5.95 into mu air, that is 1.8 into 10 to the power minus 5 divided by rho air, that is 1.2 into 420 into 10 to the power minus 6. So, answer lies as minimum fluidization velocity is 0.2 meter per second. So, it means that we must supply the we must insert a velocity to this air at a rate which is velocity of air should be 0.2 meter per second to bring this collapsed state of particles into fluidized state. So, this is all about this lecture today. Thank you for your attention.